So let's look at how this might work, let's say, for memory. So this, by the way, is the prototype exokernel called Aegis. And that was written for a MIPS CPU. MIPS was a RISC processor, so a reduced instruction set. Well, it still is. And one thing to know about the MIPS CPU, let's just take a little detour there, is that the MIPS CPU, the MMU, did not support page tables. All the MMU did was support a TLB. That's it. And so the TLB actually was managed by the kernel. So the kernel decides which entry to remove when you put in a new one. So it can use some sort of an LRU approach, or it can use a random replacement. It gets to decide that. And the TLB is basically just TLB is always a cache. The TLB here is a cache for the kernel actually to do this mapping. So what happens is on a TLB fault, kernel will add a new TLB entry covering the faulting virtual address. What's the advantage of this? Well, the advantage is that the kernel can then use whatever mechanism it wants for converting virtual addresses to physical addresses. It can use a single-level page table. It can use a multi-level page table. It can use an inverted page table. It can use any of these things that it wants is fine. And the theory on this for the MIPS was that there's no page table support. That left die space on the CPU for a larger TLB. So the theory is that the effective memory access time was about the same, right? So if you look at the effective memory access, right, that is a weighted average of the memory access in cases where you have a TLB hit and the cases where you have a TLB miss. If you have a TLB miss, the cost is much more. It's no longer 2 memory cycles. It's lots of instructions that you have to do. So that one goes up quite a bit. But on the other hand, we would hope that with a larger TLB, the TLB hit rate would be much larger than it was in the case of, let's say, the x86. Okay, so this is worth noting. And it's worth noting because keep in mind, an exokernel is designed for the hardware it's on, right? We're exposing hardware, and therefore the applications are going to be aware of what sort of MMU that this hardware has. So we know we don't have a page table, so our interface is going to be dealing with TLB entries. So the resources, so this is our background for the MIPS CPU. All we deal with is TLBs. So our resources, the kernel is going to expose physical pages and the virtual address, the physical address, MMU mappings. And what's the app to kernel API? So if we look at the system calls, we basically we can allocate a page, and that will give us back a physical address for the page. Okay, so clearly it's exposing physical pages. Of course, the kernel is going to keep track of the fact that that physical address is owned by our application. So the exokernel still has to do some sort of management of these resources. So it's going to ensure it doesn't give out a page that some other application has. Another system call we have writes to the TLB. Let's not think of it exactly that way. Let's think of it as writes a TLB entry. So the entry is going to be a virtual address mapping to a physical address with some permission. This doesn't write directly to the TLB. Instead, what happens is we've got the TLB and it's got a bunch of entries in it. So the kernel has a big set of TLB entries. TLB itself, part of the hardware, very fast access. This big one is just in regular old memory. And so on a TLB miss, the first thing the kernel is going to do is going to go to its big cache of TLB entries that it has gotten from various applications doing a TLB write, and then try to find a matching TLB entry and put it in. If it doesn't find it, then it can go ahead and call into the application, allowing the application to provide a TLB write. So anyway, this is the mapping from a virtual address to a physical address with the permissions. The other thing that we can do is we can this is for inter-process communication, we can go ahead and allow another environment access to a physical address. When we call this write command for a virtual address to a physical address, the exokernel is going to look and say, about this physical address, do you have permissions to use it? That is, did you allocate it? Or did someone grant it to you? Because if neither of those is the case, the TLB write will fail, okay? Because you don't have the authorization to make this mapping. Once it has made this mapping, it can then go in and put it in its cache of TLB entries and use it to fill the actual TLB. We also can, of course, deallocate a page. And that's all we really need here. And then we also have upcalls. So these upcalls are calls that the kernel makes to the application. So one upcall is on a page fault. We get given a virtual address, and we could get some information about the page fault. You know, things like was it read, write, stuff like that. So this will allow us to handle virtual memory. If we want to do demand paging, for instance, where we would page in our executable, then as long as our page fault code is in memory, okay, so let's assume the exokernel has made sure to load that. Then, if we get a page fault for a virtual address, we can go look at the virtual address, see that it corresponds to, let's say, an area of our executable. We can then go ahead and allocate a page. We can read from the disk, from our ELF file, into that page. We can then, once that disk read is completed, do a TLB write and write that the virtual address of our executable maps to the physical address that we read with, let's say, read-only permission since it's an executable. And that's how we can handle a page fault and do all of our paging from user mode and not from kernel mode. How does the system, how does this exokernel deal with the fact that memory may become in short supply, right? We may get a process down the road that needs to allocate memory, and it can't. So we call allocate page, and all the pages are allocated. What do we do? Well, it seems reasonable for the kernel to be managing these set of pages that each application has. We could keep track of the fact, let's say we have 2 applications, and let's just keep track of which pages are in use. So the physical pages. So application 1 may be using 3, 5, 7, 8, 9, 10, and 11, and app 2 is using 1 and 4 and 12. So let's say application 3 comes along and wants to allocate a page. Then the kernel can go and look and say, application 2's only got 3 pages. Application 1 has already got 7 pages. Let's go ahead and tell application 1 to release a page. We're not going to decide on our own, gee, 8 looks like a good page to get rid of. Okay? Instead, we are going to ask, so not only will the application know that we are deallocating that page, but also the application gets to decide what page to deallocate. So we have no idea which of these would be a better page or worse page to deallocate. Application 1 may realize that one of these pages is, let's say, an executable page that's not dirty. And so it's a better one to get rid of than some other page. Or that it's easy to recreate the contents of this page. So what the kernel will do is ask the application to please release memory. And so it'll ask for the amount to release. And so then it's up to the application when it gets this call, right? And these 2 calls are going to be happening, right? Let's look at the possibilities. The application may already be running and we get one of these calls, or the application may not have been running and we actually context switch in to run one of these calls. In either case, the job is to release the amount of memory asked for. How? By calling dealloc page. When we call dealloc page, the kernel is going to go ahead and remove from its TLB list any of these mappings. One thing about that TLB list, of course, is the list of TLB entries that the kernel has is going to have TLB entries and also note which application has created those TLB entries, because the TLB entries are only valid, of course, while that application is running, because multiple applications could have TLB entries for the same virtual addresses. So The problem here is, have we all of a sudden gone to losing the ability of the exokernel to have complete control over what's happening, right? Because it's only nicely, and it is nicely because it says please, asking for the memory to be released, but not forcing it. Well, what it can do is wait a short amount of time and see whether the process has actually deallocated memory or not. If it hasn't deallocated the requested memory, well, sure, then we can go ahead and say, well, you couldn't decide. This is sort of like dealing with a child in some ways. You couldn't decide, so I'm going to decide for you. So I asked you to get rid of 3 pages. You didn't do it. I'm going to just get rid of the first 3. So there are a variety of ways to do this, right? One way you could do it is say, you didn't deallocate the memory you wanted. I'm going to just terminate you because you're bad. A second way you could do it is you can say, I'm going to forcibly remove those pages from you. But I'll go ahead and add another op call that tells you which ones I removed from you, okay, so that you know. So that's ways in which we can deal with memory, where the application has much more control of what is going on, and the kernel is doing the least amount that it can really do. All it's really doing for every page of memory, who owns it, who has access to it, and that's really about it. I guess the other would be which TLB mappings use it. The TLB mappings are going to ensure that no process can access the pages of another process without it having been granted access. So this is all the kernel is going to have to keep track of. What doesn't it have to keep track of? It doesn't have to keep track of moving pages out to disk or not moving pages out to disk. It doesn't actually have to keep track of filling the contents of any page. All it has to do on an alloc page is return a 0 filled page. And then everything from that page on is up to the application to deal with, right? It's going to have to, can't use a physical address directly, right? You can only access a physical page via a virtual address. So it's going to have to do a TLB write to establish a virtual address with it. And then it's going to have to actually use that address and write into that page. It can write into the page from code. It can go ahead and read in from the disk, anything it wants. The only other way in which the kernel is involved is this decision of which application should free up memory when memory is getting low, right? And it can use different policies for that. One policy is certainly just give equal amount of memory to every application. But it's not deciding which pages to get rid of. The app gets to decide which pages to get rid of. It's hard to see how a kernel could do less than this in terms of protection. It has to know, it seems, for every page who owns it in order to protect from other applications accessing the pages. Let's look at some ways applications can use this user memory. So for example, the databases like to keep a cache of disk pages in memory, right? So you've got a database. So databases often have a page cache. But when we have a traditional OS, let's say that's doing demand paging, it may decide for virtual memory that it needs a page. And so it's going to take a page that happens to belong to this database. And it doesn't know any pages different from any other pages, so it may take this page, let's say. And it's going to go ahead and write it. So this is the kernel. It's going to write this page to disk. The problem is, this was a cache of what's in the database. So the database knows how to retrieve this page. That is, it's already on the disk somewhere. So if we look at it in more detail, the database has made a cache of this page. So this is in the database. Database read it in, has it cached. The kernel then says, oh, I need this page. I better write it back out to disk. I am going to go ahead and write it out to here. Well, that was a waste of time because the database, if you'd only asked it, would say, oh, just throw the sucker away. I know where to find it. In an exokernel, it'd be different. The exokernel would come in and would say, hey, database, I would like you to give me a page, please. And the database will look and will say, well, I could choose this page. Hey, this page is cached on disk. I will just deallocate it I don't need to write it anywhere. If it did happen to choose a dirty page, it would be responsible for writing a disk, and then after that, deallocating it. We have less fighting with the abstractions because, unfortunately, the fact that the virtual memory is transparent means that there is no interaction that the application has with a traditional kernel as far as dealing with the paging algorithm. And instead, by providing the actual signals of what the operating system really wants, right? What I really want is a page, then delegating that to the database to deal with. You might say, well, but it just does seem kind of stupid to have every application have all this code rewritten for dealing with page faults and handling virtual memory and so on. That's what libraries are for, right? We can have a library that has a reasonable set of defaults, and this particular database can go ahead and then change that behavior for an exokernel situation.